everyone. So today we are going to be talking about conservation of momentum. So this law of conservation of momentum basically states that if we don't have an external force acting on a system, then the net momentum can't change. So we get an equation for this. It's the initial momentum of the system will equal the final momentum of the system. Now, the focus here is on external forces acting on a closed system. So although some internal forces might occur and therefore change the linear momentum of portions of the system, they can't change the total linear momentum of the entire system as a whole. Now, depending on the forces acting on this system, linear momentum might be conserved in one or two directions, but not all directions. So if the component of the net external force on a system is 0 along an axis, then the component of the linear momentum of the system along that axis can't change. So an example of this would be tossing a ball as a projectile across a room. We know that the only force acting on that object is in the y direction, the force of gravity pulling it back towards the ground. So since there's no forces acting in the x direction, the horizontal direction, the momentum in the horizontal direction is constant. It doesn't change, right? But the momentum in the y direction does change because of that outside force. So one of the major justifications for introducing momentum is that it's going to help us predict the behavior of objects that collide. So when we have two objects that are colliding, we call those two objects the system itself. So when they collide, those forces that are happening are internal to the system. So since there's no external forces, we have the law of conservation of momentum saying that momentum is conserved. So because of this, we get that the net momentum of the system initial equals the net momentum of the system final. Now, if we're talking about two objects that are colliding, the initial momentum will be equal to the initial momentum of object 1 plus the initial momentum of object 2, and then the final momentum will be the final momentum of object 1 plus the final momentum of object 2. Of course, we know that momentum is equal to mass times velocity, so we can just plug that in here. Now, in this equation here, note that I only have initial and final subscripts on the velocity because the mass itself themselves aren't changing, right? So I have mass 1 times initial velocity of object 1, mass 2 times initial velocity of object 2 equals mass 1 times final velocity of object 1 plus mass 2 times final velocity of object 2. Now this equation right here is the law of conservation of momentum. So this is the equation that you're going to be using for a lot of these problems in this section of this unit. Now we're going to kind of manipulate this equation a little bit, and I'll show you what I mean by that when we talk about different types of collisions. So, different types of collisions. Now there's two main types of collisions, elastic and inelastic. When we talk about elastic collisions, I remember this because elastic is kind of like a rubber band, and a rubber band kind of snaps, right? It has this elastic property. Now in an elastic collision, and I say that, I enunciate that very well because there's a reason for that. In an elastic collision, objects bounce off one another. So an example of this would be billiard balls or pool table balls. Pool table balls? Now, another really important thing about elastic collisions is that kinetic energy is conserved. And because kinetic energy is conserved, we can see if a collision is completely elastic if we see that the initial kinetic energy is equal to the final kinetic energy. And I have seen this on an AP test before, how they ask you, is this collision elastic? And you have to actually calculate the initial and final kinetic energy. And then if they are the same, then you can say, yes, this collision is completely elastic. Just because the objects don't stick together at the end doesn't mean that the collision is completely elastic. And also momentum is conserved. Now in inelastic collisions, and this is why I enunciate, because in an elastic and in an inelastic collision, sounds very similar, right? So in an inelastic collision, the objects stick together in a completely inelastic collision. Now, of course, in real life, collisions are never completely elastic or completely inelastic, but we can just kind of, in a theoretical world, right, they can be. So these objects stick together when we have a completely inelastic collision, and the kinetic energy is not conserved. And again, that's a very important thing to remember because I have seen it in AP test before. Of course, in an inelastic collision, momentum is still conserved. We can use the same equation. Now, like I said, real life collisions are not completely elastic or inelastic. They're a mix of both. Usually you'll say like a certain percentage elastic, a certain percentage inelastic. Some energy is transferred from kinetic energy to other forms, such as thermal energy or energy of sound. So if we have a one-dimensional, completely inelastic collision, we can kind of manipulate that equation that we saw before and simplify it a little bit. So we had this equation before where we have the initial momentum of object 1 plus the initial momentum of object 2 equals the final momentum, so final momentum object 1 plus final momentum of object 2. Now remember, in a completely inelastic collision, the masses stick together at the end. So since they stick together at the end, we know that final velocity of object 1 will be equal to final velocity of object 2 because they're colliding and then moving off together. So because they're moving off together, that final velocity is going to be the same. So because of that, we can just say that they move away with a final velocity v, and then what we can do is we can just factor that final velocity out. So you get this simplified equation here. Now, if we have an elastic collision, remember, if this is really hard to say. If a collision is completely elastic, momentum is conserved and also kinetic energy is conserved. So sometimes they give you enough information to solve, but not enough information to solve easily. Okay, so because of that, there's actually these equations in your book that they derive for you, and I'll show you how they do it. I'll show you half of it, how they do it. And these are helpful to remember because it'll cut your solving time down, but you don't have to memorize them because there is a way to do it, to solve these problems without these special equations. It just takes a lot longer. So remember, when we have when we have a elastic collision, both momentum and kinetic energy are conserved. Now, if we have a stationary target, we'll call the target M2, mass 2. That means that V initial 2 is 0, which is why that term disappeared on the left-hand side here. So we have a stationary target in this example. So we have the initial momentum of object 1 is equal to the final momentum of object 1 plus the final momentum of object 2. Now, if this is an elastic collision, that means that kinetic energy is also conserved. Again, because the target M2 is stationary, we don't have the second term. If the target was moving, we would also have a plus 1/2 M2V initial 2 squared on this side as well, but we don't because the target is stationary. Now, what we do here is we're going to rewrite these equations. We are going to put the velocities for mass 1 on one side and factor out an M1. And same thing over here, just rewriting these equations. And then what we're going to do next is some algebra magic. Ta-da! And we get these equations right here. Now, these are in your book, and like I said, it is helpful to write these down, to have them in order to solve when we have elastic collisions in one dimension with a stationary target. Now, take a note that this is with a stationary target and it's with elastic collisions, so both momentum and kinetic energy are conserved. Like I said, it is possible to do these types of problems without these special equations. It takes longer. Okay, you have to it's going to look really ugly before you're able to actually solve. Now, some special situations with stationary targets. If those stationary targets have equal masses, so an example of that would be pool balls or billiard balls. After they collide, so if we have a stationary target, right, I have my initial velocity of mass 2 is 0. Now, if we have equal masses, mass 1 is going to come in and hit mass 2, and then mass 2 will then move off at the initial velocity of mass 1. Mass 1 will then have a final velocity of 0. All right, that's our first special situation. Our second special situation is if we have a very massive target. So say a golf ball is hitting a cannonball and the cannonball is stationary. That cannonball is here, the golf ball is coming in and it's very, very tiny compared to that huge cannonball. The final velocity of the golf ball will just be the opposite sign of the initial velocity of that golf ball, meaning it's just going to hit and then go straight back in the opposite direction with the same magnitude of velocity. And this is kind of just a simplification that we make as well. And then the velocity 2, so the velocity of the cannonball final, will be equal to 2 times mass 1 over mass 2 times velocity 1 initial. And then last but not least, if we have a massive projectile, so a cannonball, say, hitting a golf ball. So my golf ball is stationary, and now I have this huge cannonball coming in. The final velocity of mass 1, so that's the cannonball, that huge object coming in and hitting the golf ball, will just be equal to the initial velocity of mass 1. So that velocity doesn't change. And then a simplification that we make is that the final velocity of mass 2, the golf ball, the small object, will be 2 times that initial velocity of object 1. These are some special situations. Now, if we have a moving target, so this is like those special equations that I just showed you with a stationary target, but now the target is moving. So now you can see that we have an initial velocity for mass 2, so that term is present. So again, we have an elastic collision, which means that we have both momentum conserved and kinetic energy conserved. So here we're going to rewrite these. Da, 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 da. And then we are going to do some algebra magic. This is not important, but we get these crazy looking equations. All right. So because these equations are crazy looking, again, I would not memorize these. I would write them down. They are definitely helpful to have as a note in your notes. But like I said, it is possible to do problems like this with elastic collisions in one dimension with a moving target, but it's not pretty sometimes. And the reasons that these equations can be so helpful is that sometimes they don't give you enough information. Like, for example, do you see how in this first equation right here, I have a final velocity of mass 1, I have an initial velocity of mass 1, and I have an initial velocity of mass 2. In this equation right here, I don't have a final velocity of mass 2. So because of that, if they don't give me that information and I'm not actually solving for final velocity of mass 2 either, I can use this equation for an elastic collision in one dimension with a moving target and then pretty easily find what I'm looking for, because sometimes you're not given enough information. Same thing down here, I can see that I have a final velocity of mass 2, an initial velocity of mass 1, and an initial velocity of mass 2. So in this equation down here, I am not given a final velocity of mass 1. So because of that, I can use this equation when I'm not given that information and I don't want to find that information. Okay, so that's the only time that these equations are very helpful. My last example will be using equations like this to show you why they are helpful.